All right. Good afternoon, everyone. We will continue our lectures this afternoon. We are looking at some basic building blocks. We are looking at some basic building blocks with regards to digital logic circuits and binary logic. Now, by the way, if you are following the notes on Moodle, the notes on Moodle are here, but I am teaching you in a slightly different order. So we are probably sitting over here right now, okay? Right? And we'll go through these gates and I'll explain them. So yesterday we looked at the first gate, or the first particular little circuit, right, which is called the NOT gate or the inverter. We looked at the first little gate, which is called the NOT gate or the inverter. All right? And basically what the inverter does is, when you plug in a binary 0, it's got one input and one output. And when you plug in a binary 0, it will flip, right? It will flip the bit, okay? And when you plug in a binary 1, it will convert it into a 0. Plug in the binary 0, it will convert it into a 1, right? So input is 1, output is 0, as shown on the table, okay? All right. And this here is the logic symbol. Okay, let me flip over to the document camera, and let's have a look at some other gates as we go along. All right. Just to let you know that some of those notes are on the Moodle shell as well. Okay. Now, today's date is 7th. And we are on week 3. We are on week 3, lecture 3. Okay. Right. The next gate I want to talk to you about is the AND gate. Right? Now, as the word says, if you look at the name, the name gives it away. All right? When in the English language, when we use the word AND, it is an associative word, right? Which means, so if you say Peter and Tom played soccer, that means both of them played soccer. All right? So one way to remember this particular gate is with the name, you can remember that, okay, AND means that both parties have to be involved. Right? Both parties have to be involved. All right. So let's have a look at the circuit, the logic symbol. All right, that is the logic symbol, right? It's nicely rounded. Let me flip over quickly to the PC. That was my hand-drawn symbol. Let me show you the logic symbol. There we go. That's an AND gate, right? Nice and rounded. Nice and rounded. Okay? All right. Now, the truth table. What is the truth table? The truth table, as discussed yesterday, as shown in the NOT gate, it gives the behavior of input related to output. Now, looking at this particular truth table, how many inputs do we have? We have 2 inputs. And how many outputs? 1 output. Okay. So let's draw the truth table. Fairly easy. So we have a truth table. We have A, B, and we always put a double line to separate the input from the output. All right? Okay, look at how I've drawn the table. This is convention. A lot of the things which I'm writing now, the manner in which I'm writing them is convention. Convention means it is the way or the procedure in which we write it. Okay? Just like when you learned in mathematics how to do integration, you didn't write INT, right? You drew a particular symbol, right? Okay? Which means integration. So over here, this is the truth table. You have inputs on one side and output on one side, and you have a double line. You draw a double line to indicate that that is the separator between input and output. Right? That is the convention. Even though, if you write it differently, it may not necessarily be wrong, but this is the manner in which we write it, or the notation which we use. Okay? Okay, all right. Now, if there are 2 combinations, let's flip back to our inverter, when we looked at our inverter, there was one input. One input. So how many possible input combinations were there? 2, right? Either you could plug in a 0 or you could plug in a 1. Now in this particular case, there are 2 inputs. How many possible combinations can you have? 4, all right? So 0, 0, 0, 1, 1, 0, 1, 1. And how can you quickly calculate the number of combinations? You have 2 to the power of n, where n is the number of inputs. You can write that down. I'm not going to write everything down. I'm just going to show you some things which are important for the purpose of our thing. All right, now, over here. See, the difference is, if I would have showed you, if I would have taught you the AND gate directly from here, this would have been a matter of memorization. But the reason why I'm writing it down on the document camera is for you to understand the reasoning behind it. Now, if you look at 0 as let's say attendance, let's think of this in terms of attendance. Let it soccer player A, soccer player B. If there is a 1, right? If there is a 1, that means the soccer player attended the training. And if there is a 0, that means they were absent from the training, right? Okay? And eventually, the output X refers to, let's say, game, whether they'll be given a chance to play the game or not. Naturally, the rule is, if you don't train, no game. Right? You remember that? No train, no game. Okay? Or is it no pain, no gain? All right. All right. Okay. So, all right. So in line 1, in line 0, actually we call this line 0, because I want you to note this as well. 0, 0 in decimal is what? 0, right? So we always start off by calling these lines on the truth table by their decimal equivalent. So 0, 0 is 0. All right. Okay, line 0 is both players did not train. So obviously, no game. Right? And you need, let's say, you need maybe players, maybe let me substitute, let me give that, exchange that example. Let's say there's team A team and B team. Right? A team and B team. If A team did not train and B team did not train, that means none of them will play the game. Right? Okay? Now, A team did not train and B team did not train. B team trained. Right? What that means there is that, obviously you've got to have at least, maybe the player example is better, maybe at least you've got to have both players in order to play. Right? So you still don't have any game over here, because you need both. Right? The word N, remember my original definition was the word N correlates to both. So when you say Tom and Peter played soccer, it means both of them played soccer. Right. Now, when you have 1 and 0, again, one guy is missing, you can't have that. Right? 1 and 1, you have a 1. All right? So the output in an AND gate is only valid if and only if you have both inputs as 1. Let me give you an engineering example. Let's move away from soccer. Let's talk about engineering. Let us say you have an AND gate and you have 2 sensors, security sensors. One security sensor at the front door and one security sensor security sensor is not a good example in this case. Let's say you have a particular air conditioning system, right? You have an air conditioning system, and you are relying on the signal from 2 temperature sensors, right? And in order for the air conditioning system to turn on, right, you need both sensors to trigger saying, yes, we have reached the temperature. Let's say if you say 26 degrees Celsius, the moment you hit above 26, then both sensor 1 and sensor A and sensor B will trigger and tell the air conditioning system turn on. All right? So in this particular situation, if both sensors are giving 0, that means both sensors are are below 26, which means it's cool, right? If one sensor is giving 0 on one side of the room and one sensor is saying, so one sensor is saying hot, one sensor is saying cold, in our design, in this particular design, remember it's up to the designer. Remember, it's always up to the designer how they want to configure the system. In this particular design, the way I've mentioned it, it's saying that 0 is, if you need both sensors to trigger in order for the air conditioning turn on. So if in line 1, which is this line here, line 1, only one side of the room is hot, one side of the room is cold. So the air conditioner will not turn on. In this line 2, right, 1, 0, this side of the room is hot, that side of the room is cold, therefore it will still not turn on. In line 3, 1, 1, it means both sides of the room is hot, therefore we turn on the air conditioning system. All right? Okay. Now, the mathematical Boolean algebra, the Boolean algebra method to write this is x is equals to a. Can you see that dot over there? Now, it is very easy for you to think of that dot as multiply, but it is not multiply. I repeat, this is not multiply. This is not multiply. That is, in Boolean algebra, AND. A and B. Okay? A and B. A lot of times, when you start, so right from day one, I'm telling you now, and always remember this, there's another symbol which looks like a plus, right? And people call it plus or addition. But no, that will be or. So that's something separate, right? Okay? So this is dot or and. We call it AND. A and B. Okay? And we'll still do some mathematical operations on that. Now, the timing diagram. Let's have a look at something called the timing diagram. So let us say there is a okay. A, let's look at this A. A does 0, 0, 1, 1. 0, 0, 1, 1. B. B will be 0, 1. Look at the truth table as well. 0, 1. 0, 1. And obviously, our output x, if this is a 0, this is a 0, this will be a 0. This is a 0, this is a 1, will give you a 0. This is a 1, this is a 0, will give you a 0. This is a 1, this is a 1, will give you a 1. So a timing diagram is basically the same information. So the point I want to make over here, guys, is that we have four different pieces of information on the screen over here. You have the circuit symbol, the logic symbol. You have the Boolean algebra. You have the truth table. You have the timing diagram. Timing diagram is the behavior shown graphically. They are all talking about the same thing. It's just like when you were in secondary school and some of you did some drawing. When you draw a box or a house, you can draw it in isometric. You can draw it in orthographic. You can draw it in oblique. You can draw it in orthographic first angle projection, third angle projection. You can draw it in oblique, in single perspective, dual perspective. But at the end of the day, you are still referring to the same object. It's only different ways of drawing diagram of the same thing. So whether you draw it in isometric or orthographic, they're the same object. It's only your drawing is different. Your language is different, right? Or the method is different. So your circuit symbol, this mathematical, this truth table, they're all referring to the same AND gate. It's only different languages. I'm showing you 4 different languages of representing the same particular gate. Right? Okay, guys? There's a few more gates to go. I will be leaving now. I will hand over to Mr. Krish Raj. He will take the rest of the lecture, and yeah, he'll take over with OR gates. All right? Thank you. Alright guys, see you later.
Okay, hi guys. My name is Krish. I'm one of the PG students for Mr. Janif. So I'll take further for our lecture. So you guys have understood AND gate for now, right? Is it okay? So basically, you can see for AND gates, what can you see? Do you see that for your 2 inputs, whenever it's high, that's the only time your output will be high. Did you notice that? Right? So basically, he was saying that you cannot use multiplication, but our time, we did use multiplication, right? So 1 times 1, that's the only time you'll get 1, right? Other times when it's 0, with a multiplication, you'll always get 0. Set? You understand that, right? So it's a simple Boolean expression. Now we'll look at OR gate. OR gate is much more simpler than this. So OR gates will also have a 2 input, A and B, and the symbol I mean is a little bit different from the AND gate. Let's also see the one. Where is the OR gate? Okay, here. So this is basically how the OR gate looks like, right? So as you can see, he was saying that it's written as plus, but we don't say plus, okay? We always say OR. So this will also have a, let's use a different output expression for this. Let's use as Z, okay? So let's look at the truth table for this. Okay, sorry. Set, screw cut, right? So similarly for this, the truth table, A, B, right? 2 inputs, so there'll be 4 expressions, 0, 0, 0, 1, 1, 0, and 1, 1. So basically for OR gates, you will just need 1 high to get a output of high. You understand that? Right? So whenever you have one high, you'll get a Z of high. So for 0, 0, definitely you will get low, 0. You have 1 high for your B input, so you'll definitely get a 1. You have A of high, right? So you'll get your output as high, which is 1. And also for your, if both of your inputs are high. So you'll get a high. So that's a very simple Boolean expression. Okay, let's also look at the timing diagram for this and the Boolean expression. The Boolean expression for this is basically your Z equals to your input plus B. Can you see now? All good? Right? We usually make a mistake of saying it plus, but bear in mind it's O, okay? All good? You guys have jotted down? Set? All these Boolean expressions will be used in like your circuitry. There'll be like small IC chips, right? And then our electricity will be in binary language, right? So that's why we're using high and low. It will be like 5 volts and 0 volts, right? And that's how we're gonna communicate with our circuitry. You'll be seeing that in your labs, I think. Yeah, you guys have labs? Yeah. You'll be seeing many IC chips. So it's really interesting. Okay, so the timing diagram for the OR gate, right? Let's look at that. So your first input A, so a low, another low, right, low, so guys, help me out here, how our timing diagram will be. So for the first one, 0, 0, what will be? High or low? Come on, anybody? Low? Okay. And what about the next one? When it's 0, 1? High. What about this one? High. Next one, 1, 1, definitely high, right? So yeah, so basically that's it for OR expression, right? OR Boolean expression. It's quite simple. So N and O are like the basic ones. Now you'll see how they collaborate with the other small ones. So the first one, which will collaborate with O and N, is our buffer, right? Buffer will always have a one input. It will never have any, like more than one input, right? So it will just have a. It's a simple triangle. Simple inverted triangle. Right? So the truth table for this is very simple. So it just has 0 and 1, right? And basically whatever goes in from the input is just the output. So 0, 1. You guys get it? So what about its Boolean expression? Anybody can guess? Pardon? Minus? Yeah, correct. X equals A. Okay, that's your expression. Set. So you don't need a timing diagram for that, eh? It's very simple. Now it's the fun part. You guys done? Set. I'll move further. Now it's the NAND gate, okay? NAND gate is basically just the AND gate. And all the outputs for the AND gate, you'll just be inverting it, right? So I'll show you how it looks like. Okay, first I'll show it in this. AND gate. Oh. Okay, no problem. I'll show it from here. I'm not sure where in the lecture notes it is. Okay, so AND gate basically means not and basically your AND, okay? Right? Not an AND, okay? So the symbol for the NAND gate is basically your two inputs, the simple AND gate, and it will have a small bubble in front, okay? This signifies it's a NOT, okay? So there, that's how it looks like. Whenever you see this bubble, you'll know it's a NOT. Whatever your N is, you just have to invert it, okay? Another way you can see this is if you have your inputs, right? Your AND gate, you'll have your output. Let's take a variable of y, and then your buffer. Buffer with a NOT, because buffer was just whatever your input is, your output. So we just use a bubble in the buffer, right? But don't worry, you'll never have to show this one. I'm just showing it to elaborate what a NAND gate is, right? So there. So now let's look at the truth table for this. Okay, truth table. You'll simply have 4 combinations: A, B, so how was the combinations for AND gate? 0, 0 was? Anybody? 0? Please speak up, eh? Okay, 0, 1 for your AND gate was? 0. What about 1, 0? 0, 1, 1? 1. So now X is showing after this, okay? I'm showing after this. So basically, whatever your outputs are here, you'll just be inverting it, right? So your zeros will become 1, and your 1 will be 0. So that's basically it, okay? Your AND gate, you're just inverting it. Simple? You get it? You understand? Okay. Let's see how the Boolean expression of this looks like, right? This will be important for your short test and all that, yeah? You'll definitely he'll ask to like show the expression. So let's see. So let's see first for the AND gate expression. So for the AND gate is A and B, right? And then this one, it's basically X equals to your Y. This is how we write if it's inverted, okay? Not. There's a small, what do you say, a dash on top of your variable, okay? And how can you, there's a further way you can express this. So let's see. X equals, Y is A and B, right? So you can just write A and B and the whole thing. See, you get it? Simple? So the final expression for your NAND gate, you guys can see, right? Oh. Final expression for your NAND gate is X, A, and B, that basic notch. Set. Hope you understand, okay? If you have any problems, you can hands up. All good? Set, would you like to move further? Okay. Okay, just like we have seen the NAND gate, let's look at the NOR gate, right? NOR gate. So, what can you pick from NOR gate? It's basically your OR gate inverted, right? You get it? So, N is your NOT, and O is your OR gate, okay? Your OR expression. So, let's see how the symbol looks like. You basically have the same inputs, your OR gate, which is a, I don't know the symbol, there, and your notch, okay? Notch and your variable output. Let's keep it as X. Right? If you want to further elaborate your symbol, just like the previous one, NAND gate, we can see it. There you go. You can keep that, and your buffer with a NOT, and your output. Set, you understand? Please keep in mind, if you get a question to show this symbol, try to show this one. You don't need this one. This one is much more better. This one is just to understand, okay? Okay, let's look at the truth table for the NOR gate. Okay, A, B, 0, 0, 0, 1, 1, 0, 1, 1. So what was the output for the simple OR gate? 0, 0 was? Anybody? 0? Okay. 0, 1? 1. 1, 0? 1. What about 1? Okay. So now, what I've just told you, it's a NOR gate, so NOT is just going to invert your output, okay? So all your zeros will become 1, and your 1s will become 0. Simple, eh? Okay, let's, what else? Okay, let's look at our expression, right? Boolean expression. So first, we break it down. Let's look at our expression for the OR gate, okay? The OR gate first, this much. So your output is Y equals your input A or B, right? That's correct? Now let's looking at your further X output. At X, it will be X equals to your Y with that special notch I told you about, right? And if you further want to break it down, it's X, your Y expression is A plus A or B, so A or B with that notch, okay? Simple. So that's your final expression. There you go. Okay, I'll give you 2 minutes. You can copy that. So basically, these were the main Boolean expressions you guys need to know, the most important one. I'll be showing you another two, but those are not like usually used. And then from next class, I think Mr. Janif will be showing how you're gonna be collaborating different expressions like N and O, right? And then the output of the OR gate in the AND gate and what you can see. So your truth table will start to increase, right? I'll show you an example of that, but I won't teach that right now. Okay, let's look at there's one thing called a XOR gate, right? XOR gate is like exclusive OR gate. XOR gate, right? I'll tell you the logic in a while. Exclusive, and this is definitely the OR gate, okay? I think I so are the, okay, this is the XNOR gate. Here you go. This is basically how the XOR gate looks like. You can copy the symbol for that. So the XOR gate has a kind of unique logic to it. So let's look at the truth table for this. So the inputs, it will have a simple one output, and just how Master Janif uses, you try to always show 2 lines, okay, when you're writing a truth table. When I like signifies that you are showing the output now. Okay, there you go. So 0, 0, 1, 0, 0, 1, 1, 1. So we have learned that in the OR gate, you need a high to give a high output, right? In the NOR gate, it's opposite, right? If you have a high, you just have to see the output and then invert it, right? And then in this XOR gate, the exclusive OR gate, you just need one high, right? One high or one low, right? It only sees that. If it sees 2 highs, it will definitely say it's a low, right? You guys have studied diodes, right? Diodes? Yeah, it's something like a diode, right? Like when it's in the reverse, the current comes from the reverse, it tries to oppose it, right? It doesn't let it go. So it's something like that, right? If it sees 2 highs, it won't let it go, right? Okay, so it will always look at highs, okay? Just remember, it will always look at your high, your exclusive OR gate, right? So 0, 0, it will stay 0. 1, 0, it will let it go, right? It's only one high, right? So it will give a output of 1. 1, 0, it will give a output of, anybody? 1. And what about 1, 1? 2, 0, okay? That's the funny logic about this, okay? So I know it will take time, but you guys will get it, okay? Okay, and the symbol, okay, for this expression, I mean the Boolean expression, it's your two inputs. It's that OR you had, but it's a circle, okay? It's a circle like this. You guys can see, right? It's a circle like that, and the output. So this is your expression. Okay, you guys get it? All good? Okay, let's look at the last Boolean expression, and then it's already late, right? You can take your leave. So just like we saw the XO, let's look at the XNO, right? XNO gate. So you must be already imagining what the truth table looks like, okay? So this is your exclusive. That's your NOT. And that's your OR, okay? So let's see if the symbol is here. Okay, there. This is the symbol. You can jot it down. So yes, this is how the symbol looks for the XNOR gate. This is our last gate, okay? We can further simplify this gate just to understand, okay? You don't need to use this one, but I'll just show you in case. So you'll have that XOR gate, the one we just looked at, and we'll have that buffer NOT, okay? That buffer NOT, and then your X from here, okay? You can see that? This part is your XO and your NOT, okay? So last part, let's look at the truth table before you guys go. Okay, A, B. This signifies your output. First is your Y and then your X, right? So guys, how was the truth table for XO? What was the outputs? 0, 0 will be? Anybody? 0, okay. 0, 1? Right. 1, 0? Okay. 1, 1? Okay, thank you. So what do you think? What will be the output here? Opposite of Y, right? Okay, you guys get it, right? So it's 0, it will be 1, all your 1s will be 0, 1. Set. So this is basically how you can interpret your XNOR gates. Okay, let's also see the expression for this, right? Last thing. So first is the expression for our, just the XO, right? A that's Y, okay? So our X will be Y naught, right? Is it right? And then it's basically, we're just signifying Y, okay? B with that big notch there. So this is your expression for X, no. You guys understand? All good? So what are all the gates you learned today? N? Or what else? The buffer, right? Oh, buffer, sorry. What else? The NAND, the NO, the EXO, and the XNOR, right? Set? All good with that? I hope you understand. Mr. Janif will try to elaborate more, I think, in the next class. When is the next class? Next week? Okay. Okay, set. Thank you, guys. Hi, sir. How are you? Yeah, all good. We just end the Zoom, right?
Yeah,
You just.
I've got both.
Oh, okay, okay.
I've got face-to-face and Zoom.
Oh, okay, okay, that's good. So from there. Yeah.
How was it?
Oh, it was good. It's good.
Good.
Yeah, really busy. Yeah, 3 apps.
So you PGBM now? Okay.
I almost took it home.
Huh?
Almost took it home.
Ah, okay. Yeah, you can do that.
No.
Yeah.
Set?
Yeah. Thanks.
Already put everyone in groups?
No.
Not yet.
Yeah, no.
So you'll do it
That's the second one, eh? Yeah, because the first one is not a group.
individually.
Yeah. So today I had already stressed on last.